Welcome back, dear students. So in this session we will discuss about different types of hybridization with a special emphasis on sp, sp2 and sp3 hybrid orbitals. Okay, now let's begin with the topic hybridization, chapter of chemical bonding. So first of all we will consider sp3 hybridization. The ground state of carbon atom can be written as 1s2. This is a 1s atomic orbital. This is a 2s atomic orbital. This is 2px, 2py and 2pz atomic orbital. Okay, we can write the ground state electronic configuration of carbon as 1s2, 2s2, 2px1, 2py1 and 2pz0. And you can see that only up to 2s atomic orbitals the electrons are occupied or paired or exist in pairs, but in the 2px and 2py orbital the electrons are unpaired. Okay, and this type of electron configuration suggests that the divalency of carbon atom. Okay, that means the carbon can form only can form molecules with, which contains only 3 atoms. Okay, instead of in the case of methane we can see that there are 5 atoms, carbon 1 and 4 hydrogen, that means 5 atoms. But this electron configuration of carbon suggests that the carbon can form only 2 bonds with the other elements. But in the actual practice, we know that carbon exists in the tetravalent form. And for that, we found that the presence of an external agent like hydrogen, fluorine or any other element, what happens is carbon atom get excited. And during the excitation, one of the electrons in the 2s orbital get excited to the vacant 2pz orbital. And now see the configuration. Now we can see that the carbon atom in the excited state can have 4 unpaired electrons. Okay, and we can now we are able to explain for the tetravalency of carbon atom in molecules. But there is one more problem, that in all the carbon molecules, that means in all the saturated hydrocarbons of carbon atom, bond length remains the same. There is no difference in bond length. But here you can see that the 2s atomic orbital is spherically symmetrical, whereas 2p orbitals are dumbbell shaped. That is, they have directional properties. That which would suggest that carbon can form 2 different types of bonds. Okay, that means the bond length remains does not remain the same. But the experimental evidence shows that carbon forms equivalent bonds. So for that, Linus Pauling introduced the concept of hybridization. Here what happens is one 2s orbital and 3 2p orbitals hybridized to form 4 sp3 hybrid orbitals, 4 sp3 hybrid orbitals of equivalent energy and identical shapes, and these are directed towards fixed position in space. Okay, so during the formation of methane, what happens is, this is the sp3 hybrid orbitals of methane, and each of these sp3 hybrid orbitals then combines with the 1s atomic orbital of hydrogen atom, which contains an unpaired electron. So this results in this configuration. So we can define sp3 hybridization as 1s orbital and the 3p orbitals of the same atom mixed to form 4 identical hybrid orbitals, which arrange themselves in a tetrahedral way with an angle of 109.5 degrees between them. ചില ടെക്സ്റ്റിനകത്ത് you can see then some other text it is written like this 109 degree 28 minutes. Okay, and the bond angle here it is 109.5 degrees. Okay, so these are the 4 sp3 hybrid orbitals, and during the formation of methane, this is the sp3 hybridized carbon atom, and these are the 4 hybrid orbitals. This will combine with the 1s atomic orbital of hydrogens and leading to the formation of methane molecule. Okay, and this has tetrahedral geometry. Now let's see sp2 hybridization. Carbon atom, this is the speciality of carbon. Carbon exists in some 3 different types of hybridized state. Okay, first one is sp3, then sp2, and another one is sp hybridization. Now let's see what is the sp2 hybridized state of carbon. Okay, here this is the electronic ground state electronic configuration of carbon, and this is the excited state configuration. And what here during sp2 hybridization, what happens is 1s and 2p is a 2p orbitals hybridized. Okay, and this is the condition, and these 3 are the sp2 hybrid orbital. Okay, 1s and 2p orbital, and there is one unhybridized p orbital. This is the unhybridized p orbital. Okay, and this is the electronic configuration of ethylene molecule that we will see a little later. Okay, and so we can define sp2 hybridization as follows. Here 1 s orbital and 2 p orbitals of the same atom mixed to form 3 identical hybrid orbitals lying in a plane with a bond angle of 120 degrees between them. And this is the structure, that is trigonal planar structure. Trigonal planar structure. And in the case of ethylene molecule, what happens is this is one of the sp2 hybridized carbon atom, and this is another sp2 hybridized carbon atom. Okay, and this sp2 hybrid orbital of this carbon atom that's overlapped with the sp2 hybrid orbital of another carbon atom, leading to the formation of carbon-carbon sigma bond. This is a very strong bond, and remaining 2 sp2 hybrid orbitals of each carbon atom combines with the 1s atomic orbital of hydrogen atom. Okay, this is the case, and these are also sigma bonds, and we know that each carbon atom, each sp2 hybridized carbon atom has an unhybridized p orbital lying perpendicular to the plane, and they overlap sidewise and leading to the formation of pi bond. So these are the pi bonds. Okay, so in the case of ethylene we can write it as we can draw it as CH. Okay, like this we can represent. Single bond always represents a sigma bond, and double bond represent one sigma bond and another one it should be pi bond. Okay, so this is the case with the ethylene molecule. Now let's see BF3 molecule, sp2 hybridization in BF3 molecule. This is the boron in the ground state electronic configuration, and during the excitation what happens is one of the 2s electron get excited to the 2p orbital, and in the next step hybridization, sp2 hybridization takes place. Okay, and leading to the formation of 3 sp2 hybrid orbitals of equivalent energy and identical shape, and here there is no unpaired electron, and during the formation of BF3 what happens is the electrons unpaired electrons get paired with the 2p electrons of fluorine atom. Okay, and this is the structure of BF3 molecule. Here the boron atom, and it combines with the fluorine atoms. This green color ball represents fluorine. Okay, so this is the structure, and making the bond angle is by 120 degrees. Okay, I think now it is clear for you. Now let's see sp hybridization. Here you can sp hybridization. You can see sp hybridization in alkynes. Okay, similarly C triple bond N. Okay, here the carbon atom is in sp hybridization. Okay, an alene molecule. See, this is the alene molecule. Here the carbon atom is in, this carbon atom is sp hybridization, but these two carbon atoms are in sp2 hybridization. Okay, so now let's see the electronic configuration of this carbon atom. Here this is the electronic ground state electronic configuration. During the excitation, what happens is one of the 2s electron get excited to the vacant 2p orbital, and now 4 unpaired electrons are available, and during the formation of sp hybrid orbitals, what happens is one of the 2s electron and one 2p electron, one 2s atomic orbital hybridized with 2p orbital, leading to the formation of 2 sp hybrid orbitals, one 2s and one 2p. Okay, and there are two unpaired or unhybridized p orbitals. And this is the electronic configuration of ethylene after hybridization. Okay, now we can define sp hybridization as follows. Here during sp hybridization, what happens is one s orbital and one 2p or one of the 3 2p orbitals of the same atom hybridized to give 2 identical orbitals called sp orbitals lying linearly, making an angle of 180 degrees between them. So here you can see the hybridization pattern, and during the formation of acetylene, this is the molecule acetylene. You know the structure of acetylene. Okay, and here these are the sp hybridized carbon atoms. These are the 2 sp hybridized carbon atom. One of the sp hybrid orbitals of this carbon atom combines with or overlap with the sp hybrid orbital of this carbon atom and forms a sigma bond here, and the remaining sp hybrid orbital on each carbon atom combines with 1s atomic orbital of hydrogen, forming CH2CH sigma bonds. Okay, and we know that there are 2 unhybridized p orbitals. They are lying perpendicular to the plane or perpendicular to the molecule, so they overlap sidewise. Leading to the formation of 2 pi bonds. Okay, so in acetylene, there is only between these 2 carbon atoms there is only 1 sigma bond and then 2 pi bonds. Okay, now let's see the sp hybridization involved in beryllium difluoride molecule. Now this is the ground state electronic configuration of beryllium. Here This is the 1s orbital of beryllium, which contains only 2 electrons, and the 2s orbital of atomic orbital of beryllium contains 2 paired electrons, and the 2p orbitals are vacant. Okay, but this suggests that beryllium does not form any molecules. Okay, because all the electrons exist in the form of paired condition, but we know we know this molecule. Okay, this BeF2 molecule is existing. Okay, this is a stable molecule also, but we can't explain the existence of beryllium difluoride on the basis of this electronic configuration. So it is suggested that in the presence of fluorine atom, what happens is beryllium get excited, and during excitation one of the 2s electron get promoted to vacant 2p orbital. Okay, and leading to this electron configuration, and after that these two orbitals, that is 2s orbital and 2p orbitals, get hybridized to form 2sp hybrid orbitals of equivalent energy and identical shape. And after that each of these two sp orbitals overlap with a pz orbital of fluorine atom, 2 fluorine atoms, and forms 2 sigma bonds. Okay, so this is the structure of beryllium difluoride. This is the beryllium atom, and it will combine with a p orbital of 2 fluorine atom, and they are oriented in a linear fashion, or beryllium difluoride is a linear molecule. This is the structure of beryllium. Okay, structure of beryllium, and the bond angle is 180 degrees. Okay, and now let's conclude the discussion on sp2 and sp3 hybridization. Hope you have enjoyed the lessons. So thank you for watching. Have a nice day.